All right, let's dive straight into this explainer. If you're currently scrambling, cramming for your grade 11 chem exam, take a deep breath because you are in the exact right place. We're going to distill everything you absolutely need to know about acids and bases into a visual, easy-to-remember cheat sheet. Let's get you completely prepared to ace this test.
So we'll kick things off with a real-life hook, just to show you why any of this actually matters outside the classroom. Have you ever wondered why your eyes suddenly start stinging in a swimming pool? Well, back in May of 2001, 49 people got incredibly sick at a dance festival in Dauphin, Manitoba. The source? It was traced directly back to the hotel pool. It turns out balancing pool chemistry is a high-stakes game of health and safety, not just about keeping the water looking pretty.
Here's what's happening. To keep a pool safe, managers add sodium hypochlorite, and that forms hypochlorous acid in the water to kill off organisms. But if that water ends up with way too much acid, it violently stings your eyes. And actually, it gets worse. It'll quite literally react with the concrete walls of the pool and eat away the mortar between the tiles. So this brilliantly illustrates why pool managers have to obsessively monitor for that perfect sweet spot, right between 7.2 and 7.6. Okay, here is your cheat sheet blueprint. We're covering 1. Meet the pH scale, 2. Acids versus bases, 3. The power of 10, 4. Litmus paper and indicators, and 5. pH in the real world. Let's jump in.
First up, Section 1. Meet the pH scale, the 0 to 14 journey. Let's set the ground rules for how we actually measure these solutions. Grab a pen because you'll definitely want to write this down. The term pH literally stands for potential of hydrogen. It's the universal numerical scale we use to classify whether an aqueous solution is acidic, basic, or neutral. Basically, it reflects the exact concentration of hydrogen ions, which you write as a capital H with a little plus sign floating around in a solution.
Think of the scale like a giant playing field that ranges from 0 to 14. Step 1. Anything falling under a 7 is classified as an acid. Step 2. Pure water lands dead center, a perfectly neutral 7. And Step 3. Anything sitting above that 7 is considered a base, which you'll sometimes hear called alkaline. Moving right along to Section 2, acids versus bases, the matchup. If you're going to be tested on their properties, you've got to know how these opposing teams stack up. To lock their properties into your memory, picture this stark contrast. On one side, we have acids. If you were to taste a mild one, like a lemon, it would be super sour. Chemically speaking, when dissolved in water, acids produce those hydrogen ions we just mentioned. And a quick warning, strong acids will absolutely burn your skin. On the flip side, we have bases. They taste bitter and actually feel incredibly slippery to the touch, kind of like a bar of wet soap. Instead of hydrogen ions, bases form hydroxide ions, written as OH-. And just like those strong acids, strong bases, yeah, they can also severely burn your skin. All right, Section 3, the power of 10, the trick question. Listen up closely right now, because this is the exact spot where students always get tripped up on the exam. So the pH scale was actually suggested way back in 1909 by a Danish chemist named Søren Sorensen. He realized we needed a much better, more accurate way to describe acid concentrations. The trick here is that the pH scale isn't just a standard, simple ruler, it's a logarithmic scale. That means the concentration of hydrogen ions associated with any given value on the scale differs from the one right above or below it by a power of 10. Every single time you move just one whole number, the concentration changes tenfold. Let me put that into perspective. Let's say you're looking at a solution at pH 5 and another at pH 4. The pH 4 solution has 10 times more hydrogen ions. Easy enough, right? But what if you compare that pH 5 to a pH 3? You've moved 2 spaces. 10 times 10 is 100. So a solution at pH 3 doesn't just have slightly more hydrogen ions than a pH 5 solution, it is literally 100 times more concentrated. Definitely burn that into your brain for test day. Which brings us to Section 4, litmus paper and indicators, testing unknowns. Most common acids and bases are completely colorless solutions. By just staring at a beaker of clear liquid, you literally have zero idea if it's pure water, a highly dangerous acid, or a powerful base. Now, one surefire way to solve this mystery in the real world is by dropping in an electronic pH meter. These handy gadgets use the electrical properties of a solution to spit out a highly accurate, real-time number. They are an absolute game changer for working labs. But on your written school test, you're mostly going to be asked about visual indicators. The most famous visual indicator, hands down, is litmus paper. And hey, here's a random fun fact for your memory bank that might just snag you some bonus points. The litmus paper you use in chem class actually comes from lichens. These lichens are super important to the Canadian ecosystem, and as it turns out, they are the largest part of the winter diet for barren ground caribou. How wild is that?
Okay, here is your indicator cheat code. Litmus paper usually comes in little red and blue strips. If you dip it into an acidic solution, the blue litmus paper turns red. If you've got a basic solution, the red litmus paper turns blue. Neutral solution, neither paper changes color. So just remember the mnemonic. Blue to red means acid, red to blue means base.
But here's the catch. Litmus paper only tells you if something is an acid or a base. It totally leaves you guessing on the specific pH number. When litmus just isn't precise enough, we introduce chemical indicators that shift color at very specific pH ranges. For example, methyl orange flips from red to yellow between 3.2 and 4.4. Bromothymol blue goes from yellow to blue between 6.0 and 7.6. And phenolphthalein, that one magically turns from colorless to pink right around 8.2 to 10.0. By dropping a bit of these into an unknown solution and watching the color change, you can really narrow down exactly what you're dealing with.
Finally, Section 5, pH in the real world, the final exam. Let's take all these abstract chemistry concepts and anchor them to the stuff sitting in your house right now.
Lock this quick list in your mind, way down at the dangerous, highly acidic end, sitting between a pH of 1 and 2, you've got the gastric fluids inside your own stomach and lemon juice. Moving up toward neutral, milk sits slightly acidic, right at pH 6. Pure water is your perfectly safe, neutral haven at exactly pH 7. Crossing the line over into bases, everyday eggs and baking soda are mildly basic at a pH of 8. And then topping the charts as highly dangerous, corrosive, slippery bases, you'll find household bleach and oven cleaner lurking at a pH of 12 and 13.
Honestly, the coolest thing about all of this is that you don't even need a lab coat to find acids and bases. The sour bite of your morning tomato, the slick, slippery feel of the soap you wash your hands with, that is pure chemistry in action. You are literally interacting with the pH scale constantly throughout your entire day. So, I'm going to leave you with this final provocative thought. Your textbook points out that extracts from everyday fruits like pomegranates can actually act as natural pH indicators, completely changing color based on acidity. If the everyday foods in your fridge have their own hidden pH secrets, what crazy chemical reactions are you eating every single day? Like, what color do you think your favorite meal would turn if we tested it right now? Keep that curiosity alive, review this explainer a couple of times, and you are absolutely going to crush that chemistry exam. Thanks for hanging out and happy studying.